Our first speaker this afternoon is Dr. Tony Badrick, and Tony's been introduced previously. He's current president of the APFCB. He's the CEO of the RCPA QAP. And so Tony's going to talk on patient data moving average. Thanks, Tony.
Thank you, Peter. Yep. So I've titled it Quality Control and Moving Averages, because I think moving averages is a solution to some quality control problems. So what I'm going to talk about today is the quality control. What's quality control all about? Conventional QC, what are the limitations with conventional QC? Patient-based QC, the moving averages and other things, and perhaps I'll have a go at the future. They want me closer? Okay. So let's think about what's the purpose of quality control? What's a quality control system? Well, the purpose of a quality control system is to identify a situation where erroneous results could be reported. So it's all about reducing patient harm. It's all about risk. Okay, so it's a key aspect of risk. So what's a quality control system? Well, there's a couple of components to quality control. One is understanding error. You're only going to search for something that you know or you think is there. So the first thing you need to know is what are errors? What errors are we trying to determine or find with our quality control system? How do we detect this error? Okay, we've now got an idea what the error is. How can we find it? And really, when you think about it, if you look at manufacturing control, quality control, they can weigh every widget that comes off the end of a production line, so they can actually test everything that comes off the line and see that it's in specifications. We can't do that. We have to have a different system where we use a discontinuous QC process. We need rules that flag when we're out of control. We need an action to fix the problem, and we need to verify that we've actually identified and fixed the problem. And then we need to ensure, remember, this is all about patient risk. We need to ensure after we've done this that in fact we've identified, fixed the problem, then made sure that there were no patients' results that have been affected. So we need to identify the ones that might have been, amend them, and contact the clinician if necessary. That's the bit that most labs don't do, or they don't do it very well. We become fixated with QC, and we love QC, but we forget what the purpose of it is. So an understanding of errors. So this is the first thing. What errors are we actually looking for? It's the very core, because you're not going to find what you're not looking for. Okay? You're only going to find things that you're looking for, because if you don't, you'll call it something else. So the sort of errors that we're looking for, it's really the core of our QC system. We've adopted a Gaussian approach because it's easy. Gaussian distributions are easy. There's only two variables, the mean and the SD. And it's a nice symmetric curve, and we use Gaussian statistics for everything that we use because it's so simple, and it works most of the time. So the two areas that we look for are bias, when there's been a shift in the assay from one place to another, or imprecision, where the SD gets wider. So all our rules, when you think about it, all our current rules are based on finding a bias or imprecision. Because there's no other sorts of error, are there? Are there? We would know because we're not looking for them. And this is built into the total error concept, where the total error concept is based on bias plus SD. In fact, it's based on linear regression. So conventional QC. So this is all about how do you detect this bias or this imprecision. And really, as I said, because we don't sample every patient sample to see that it's in control, because we would know, we use a synthetic sample that we put in every now and then, and we use the results of that synthetic sample, that QC sample, to tell us whether there's a problem. So, how often we run that QC sample determines how effective the QC system is. If we only ran the QC sample once a year, that would be the only chance we ever had to show there was a problem. If we wanted a perfect QC system, we would run a QC sample after every patient. But that's not practical. So, how often we run the QC sample and where we run it is the basis of our QC system currently. So the risk, the patient risk, the risk that incorrect results going out is completely dependent on how often we run QC samples. What can go wrong? What can go wrong with that? Sounds pretty okay, doesn't it? Well, there are actually errors associated with the QC sample itself. So there's another set of errors. The material might not be commutable. I said the frequency is critical. The rules are based on the mean and the SD of the QC sample. You know, how good is the SD? And there are errors associated with actually handling the QC material itself. This is from a paper that I'll talk about a little more. And it really looks, this was published in 1998, but the data is still relevant today. It was based on one of the largest studies that I'm aware of that's been done into QC processes, QC practice. It's done as a big cap survey where they looked at 500 laboratories and they looked at their QC processes for these 4 measure-ands: calcium, cholesterol, digoxin, hemoglobin. And what was the commonest error that they found? Random error. So random error accounted for about 80% of the errors. So what's random error? Random error means that if you do it again, you won't find it. It's sort of ghostly. It's not imprecision. Remember, that's one of the areas we're looking for. It's not bias. That's the areas that we're looking for. It's something out there. It's something in the ether that we can't explain. As a scientist, doesn't that worry you? So this is the data from that survey, that extensive survey. And you'll see here that they worked out what an ideal error rate would be based on the rules that these labs were using. And you'll see that there are 2 things that they measured. A retrospective rejection rate. So this is looking at the runs, those 4 measure-ands, looking at the runs and seeing how often they rejected a run and looking at the probability of that being ideal. They did it retrospectively. So they actually went back over old data for 3 months, I think it was, and saw how often did they actually reject a run. And then they did it prospectively. So from this point onwards, they said, we're now going to look at every time you reject a run and we want to see your data. So this is what you did, historically. This is what you're going to do from now on for 6 months. And they compared the error rejection rates. And you can see here that they're different. None of them, or almost none of them, reached the ideal statistical number. But strangely enough, when people are watched, when people have to record data, they behave differently. That's interesting, isn't it? So, what the authors suggested that this was due to is how stringently laboratorians followed and recorded their policies and procedures. When you're watched, you tend to follow your procedures more so than when you look historically back and see what you actually did. So there's something. People don't follow SOPs. Doesn't matter. These are just patient results, aren't they? Where's the risk there? How often do people repeat the control? So the QC goes out. What's your first reaction? Repeat the control. Why would you do that? Why would you do that? What happened? What was the most commonest cause of error? Random error. 80% of the time, repeat the control again and it's in control. Okay, so the problem isn't with the assay, the problem is with the QC material. All those things that I said, if you repeat the QC sample, you get a different result. That's scientific, isn't it? Where did that come from? You know that though yourself, don't you? You run the QC sample and most of the time it comes back in. In fact, running the QC sample again is the most powerful QC rule there is. So there were very low rejection rates. 95% of the problems were overcome just by rerunning the QC sample. This is another consequence of this, is that people don't trust QC. You know, if it's out, if I rerun it, it's going to come in, no problems. You wonder whether or not they're using the right SD. People often don't use the correct SD. They come up with some other SD. Other errors are caused by the actual material itself, and say the majority of errors, and it's because of the preparation of the material, the storage, evaporation because they left the lid off, or there's deterioration. But I say frequency is the key to determining how good your QC rules are, as well as being aware that there are problems with the material. So, this is a survey that was done by Sten Westgard a few years ago, 2019 I think, and the question he asked of these labs, 262 labs, he asked, where do you run your controls in your run? And a significant number of people, like 50%, put the QCs at the beginning of the run. Okay? So they did a calibration, ran the QC, and then tomorrow they did another calibration, ran the QC. They never ran the QC at the end of the run. So they will never know if yesterday's run worked. Okay? How often do labs run QC? Every shift, you know, it's once every 8 hours, twice a day, 3 times a day, once a day. Most people run their QC once a day, no matter how big the run is. And remember, how good your QC strategy is based on how often you run this QC material that 80% of the time gives you an error when it's not there. So I think it's like being in a tunnel. You've got no idea what's going on. Somewhere up there tomorrow, there's a QC sample coming. If it fails, I'll ignore it because I know it's wrong most of the time. So what's wrong with conventional QC? It's convenient. It's easy. We understand it. So patient-based real-time QC is an alternative. It's been around for a long time. The haematologists have been using it for a long time. There's just been, the last 10 years or so, there's been a lot more theory and thought gone into it to validate what it's actually all about. There's lots of reviews out there. Basically, if you choose one of the models, which is moving average, you just take the average of your patient sample results. You might exclude high results, you might have some other exclusion criteria based on award or whatever, but you're basically just taking a block of results, meaning the results, or taking the average of those results, the median, and you're using that as an indication of whether the assay is in control. Okay, you get a new value in, you drop the last one off, update the median or the mean. Okay, so that's completely based on your population. So as long as your population doesn't change, it's amazingly how robust those medians and means are. If your population doesn't change and your median does change, quite likely it's going to be because there's a problem in your assay. And patient-based real-time QC works really well if you don't have QC material that's available, and that's what drove the haematologists to using it in the first place. If you may have a pre-analytical issue, such as hemolysis, if there's been a history of critical, rapid onset of error, you know, you can't wait for the QC tomorrow to tell you that you're out of control, and for low sigma value assays. There's a number of papers that I'll mention here. I'm happy to give this talk to anybody who wants it. There are advantages and disadvantages. Of course, you know, patient-based real-time QC is not perfect. Don't let me say that. But don't think that conventional QC is the gold standard. It's a very rusty in the gutter tin standard. And we all know it's comfortable, but it doesn't actually work that well. What saves us is the assays that we use are so robust. They're so good, you don't need to run controls. Because remember, we don't. We don't run effective controls. So, when you optimise patient-based moving averages, I'm just skirting through the principles of moving averages and patient-based real-time QC. And there's a workshop tomorrow being run by the MACB that Ping is going to run, where he's going to give some examples and some software for you to learn more about this. So, you know, this is moving from the theory to today to the practice tomorrow. So you'll hear a lot of this again. So these are some bias detection curves which are used to optimise patient-based real-time QC. You have to use simulation. You really have to use your patient data, and you have to insert into a control situation, you insert increasing levels of bias, both positive and negative bias, and you use some software to identify what's the optimal number of patients that you need to average to get optimal bias detection. Do you have to exclude any results? What are your limits going to be to detect this bias? So it's based on your population. So you have to be sensitive to the fact that your population may in fact change during the day. ICW in the morning, outpatients in the afternoon. During the week, more males on Monday and more females on the weekend. You'd be amazed what happens in hospital data. Seasonality because of summer and winter with some measurands. And while it's patient-based real-time QC, it's starting to take effect. So there's lots and lots of papers that are coming out now of variations on patient-based real-time QC. It doesn't just have to be moving averages or means, but there are lots of papers in lots of situations that show that it works. And generally speaking, it works as well as conventional QC. So I say there's lots of papers out there now with variations on the model. So the models can be more sophisticated than just a moving average. And there's even now some, not surprisingly, some AI and machine learning variations on patient-based real-time QC that are coming out. And there's certainly at least one instrument manufacturer that's looking at putting an AI neural network model software in their analyzer. It's not perfect. And the biggest limitation we've got currently is the software. Suitable software is just not available on board or in middleware. But we're working on that, and you'll see something of that tomorrow. So it's not readily available. It doesn't have simulation software. You need to use your patient data. You can't use somebody else's. It's so specific for many measurands. There's not really a good understanding of patient-based real-time QC yet. But there's not a good understanding of conventional QC yet either. We take so much for granted. So we don't understand about subpopulations, sex will affect it, age will affect it, as I said, environment. So in the short term, we probably will use two systems. We'll stick with what we're comfortable with conventional QC, and we'll run up patient-based real-time QC in the short term. Certainly patient-based real-time QC, patient-based, no commutability. It's great for detecting variations in lot-to-lot reagent changes. So that's a good place to start. The manufacturers are doing work on putting software on board. So far, I don't think any of it's terribly successful. This is an old table from a couple of years ago, but there are efforts to do something. Okay, remember I said there's only two forms of error, apart from those random ones that represent nearly all the errors you'll ever find. There's only two forms of error, conventionally. This is another form of error. This was when somebody was working up patient-based real-time QC, and they noticed, this is what a patient-based real-time QC moving average plot looks like. It's just like a Levy-Jennings chart. Pink's out of control, green's in control. This is over a couple of days. This was sodium measurements in an ICW, and you can see up the very left that it goes out of control. It goes into the pink for quite a few patients. I think there was about 30 patients in ICW where their sodiums went out of control. These patients, these are real patient results, moving averages, and these results were significant. So when they found out that there was an error, these results were significant. A control was run during the day, okay, where the green is, so the control was in control. They saw this data, they called a technician in to have a look at the equipment to see what was going on, and you can see it gets a bit noisy again when they run more samples, and then it goes out of control on the right-hand side again. So what was happening here was there was a mechanical defect in the instrument. There was some sort of piston or something that was sticking. The machine was going out of control for a while, coming back into control. Going out of control, coming back into control. And the patient results were affected clinically. You would never know unless you ran a QC sample after every patient. That's another sort of error that occurs. This has been suggested that could happen before, so there's more to our lives than just bias and imprecision. There are other errors lurking out there. And one of the things you see with patient-based real-time QC is because you get so much data, you can actually see that there are more errors going on. So this is just now going on. So we've solved our problem. Okay, we're talking about QC here, not just patient-based real-time QC. How do you, and this is again from that Westgard survey, how do you troubleshoot your problem? If you get a problem with QC, what do? Repeat the QC, of course. Most of the time that'll solve it. Do you do any other sort of troubleshooting? Most people do some troubleshooting. This is from that original survey. Again, looking at policies, looking at laboratory policies and what people actually do, the percentage the percentage of labs whose policy was to repeat all patient specimens with rejection, you can see what that is, 39, 39, 62. The percentage who actually did it when there was a failure, 10 instead of 39, 11 instead of 39. So again, people have policies that they don't follow. Not just in terms of QC data or QC rules, even when there's a problem and their SOP says repeat the patients, many times they don't. Okay? So you ignore the QC. When you find there's a problem, you don't do anything about it. You don't repeat the patients. How do laboratories retest patient samples? And again, retest all patient samples, don't know, 2%. Other, 27%, people don't know what they're doing. They find a problem, they don't know what they're doing. Are you worried yet? So what's the future? I think the only future is that, I hate to say it, but human beings are really bad at doing this. Humans are not good at QC. Humans are not good at repeating patient samples. Humans are not good at amending results. Humans are not good at phoning results. Humans really aren't good at this sort of stuff. So we shouldn't do it. We should take it out of our hands. We're just not trustworthy. So that comment up the top was from that paper from about 20 years ago. Developing QC methods that rely less on traditional analysis of control materials and more on internal instrument checks and patient results as indicators should be used. So they were predicting or pushing patient-based real-time QC 20 years ago. I think there should be automation in laboratories. So, we can do lots of things with our analysers currently. Can store samples, retrieve samples, rerun samples, do QC. I think we should let the instruments do everything. So I think that there should be on-board software that allows auto-verification, quality control, delta checks, anion gaps, look at instrument flags, do automatic recalibration, automatic retesting. That's the automation of the future. We're just not trustworthy. We just don't do this stuff. And remember, we're not talking about fun, we're talking about patient risk. So, in summary, QC has become in many laboratories poorly understood and practiced process relying on compliance. Tick the box rather than actually understanding why we're doing it, or anything to do with patient risk. Nothing to do with it. A patient-based real-time QC, in many circumstances, promises better detection in real time. Hybrid QC is likely to be a short-term solution because we don't like to let go. And there's a lot more we can learn about what's going on in our assays than we currently know. And we need to be open to change. So this was a quote from Curtis Parvin a few years ago, planning statistical quality control to minimise patient risk. He said, it's about time we re-looked at all this. Thank you. Oh, really? Oh.
One was copy of the slide over. Do you want to read that? I'll just read out a couple of the questions while we're changing.
Yep.
So one is, how can you troubleshoot quality control issues in haematology when calibration cannot be performed solely on one parameter, unlike chemistry?
How can you troubleshoot control when calibration cannot be performed? I guess when you say, so you've got a quality control situation that's out of control, how do you find out, well, you've got to identify what the problem is first. Presumably you've got some idea when a control fails that you have some process to try and identify what the problem is. What you want to know is, am I back in control? I think the best way to ensure you're back in control is to find some patient samples when you were in control and rerun them. Patient samples are really our best evidence when we're in control of getting consistent results because there's no commutability issues.
This is about access to slides, which
Yes.
they will have.
Yeah,
Somebody just
I'm happy to give my slides to anybody who wants them. Oh. This is about implement patient moving average for complete blood counts in paediatric hospitals with hemato-oncology patients. This is really, really difficult. It's really hard to implement these sort of rules when you've got a population that can vary as much as it can in paediatrics. There's that big range of ages, so it really doesn't work, unfortunately, for paediatric situations.
Those all relate to the previous sessions, as far as I can see. Yep.
Okay,
Okay. Yeah.
thank you.
Thank you. There are still some questions from the previous session. If we have time, we'll come back to those a bit later.